All right. To understand the program behavior at runtime when it executes on processors, we can use measurement tools to understand the time that it takes to execute a basic block or any program segment. There are several techniques to do that with varying accuracy. We can use instrument code to sample CPU cycle counters. This instrumentation code are used to query the hardware counters on the CPU. Most of the modern CPUs have some sort of CPU cycle counters you can read. You can refer to the process documentation for the assembly instruction and how to use these instructions. So these instructions have to be inserted to your program. That's often done in the compilation phase. You can specify that you want to add such profiling or instrumentation code to your original program task. And it's relatively easy to do. The second way to measure the runtime is to use simulators. In this case, we need to have a cycle accurate simulator for a particular processor. And that's very useful if your hardware is not ready or available, especially for new products. This is the method that chip designer and manufacturers, vendors have used quite some time, including the researchers in academia. These cycle accurate simulators are built for that purpose, to understand a very fine-grained and detailed execution behavior of a software on a hardware architecture. The third method is to use logic analyzer. This is non-intrusive, more accurate, but of course its setup can be complex. You essentially use circuit level signals to understand how instructions are fetched and data are fetched. You can set up traces and catch patterns to measure whether a particular point of the program has been executed or not. It's very accurate. There's some also, same time, some issues that you need to be aware of, some pitfalls for runtime measurement. The instrumentation will incur small overhead, so you don't want to just measure a few lines of code to understand how many cycles it takes, because there could be a lot of variations. You would like to measure long enough code sequence to compensate these instrumentation overhead. If you have a small program you want to measure, you may want to repeat that program for 20, hundreds, or even thousands of times to make the overall execution time much longer than the instrumentation code itself. In this way, you can amortize the instrumentation code overhead. Also, you need to be careful about multitasking effects. Those counters keep going even when task is swapped out, is not active. You will need to do multiple measurement and using some machine learning methods to pick the best result to estimate the runtime. Also, multi-core hyper-threading to ensure you must ensure the task is locked onto a single core. Otherwise, the cycles you measured is not reflecting the true behavior, because the task might be migrated to a different processor, and that's going to be off from your measured data. Also, there are power management effect. The CPU speed may change, so you cannot reliably using the cycle count to calculate the time. Normally, if a CPU operates at a fixed frequency, if you know the number of cycles, then you can calculate the time. But if your CPU speed has changed due to power management policies, scaled up or scaled down, then the timer could be different, and the number of cycles may not be useful to calculate the true execution time. There are some worst case execution time estimation tools. There are commercial tools and also research tools. Some tools, for example, game time, combines machine learning with automated theorem proving technology to give you high fidelity of the estimation. Also, they use graphs and also the integer linear programming ideas we talked about. We'll not go into a lot of details here. This is a very quick visual explanation of what's happening in the game time tool. Given the input program that you want to analyze, will generate control flow graphs using unrolling and inline functions, those techniques, to eventually have this control flow graph. This one that we saw earlier, this captures the possible paths and also the basic blocks. It will extract feasible basic paths using test cases and get ready for combining with the other part of the analysis, where we use measurement to understand the execution runtime behavior on the processor, and then use machine learning algorithms to combine these two, finally to predict the timing properties of this program, the worst case distribution, etc. There are some open problems, for example, architectures, processors are getting much more complex. Can we create processor models, and we can we change the architecture to make timing analysis easier? Also, analysis methods are brittle. Some small changes of code may require completely redoing the whole computation, like the game time that entails. So the research is going on to address these challenges. Okay, in the next few slides, I will just give you some concrete examples about how to use cycle counters to understand, measure, or estimate the runtime behavior of a program segment. Most of the modern systems have built-in registers that are incrementing every clock cycle. That's very useful if you want to use these cycle numbers to accurately measure the execution time, provided that the frequency of the processor does not change during your measurement. We'll use special assembly instructions. For example, on Intel's machines, there's a 64-bit counter. You use RDTSC, that means read timestamp counter instruction, and that will use two registers, EDX and EAX. Those two registers together, they give you a 64-bit value of the cycle count. And for newer machines, there's wraparound time. It depends on how many bits you will have. That might give you totally different range of time that you can measure. So let's look at this code here. This is a kind of a template. You can use these two variables in your code. Let's assume it's C to record the cycle count. You access the counters using a API called access counter, and you give the high register and low register to record the counters, the cycle number. And inside this API, you use the RDTSC, this assembly language instruction. You call this assembly language instruction, and this instruction will retrieve the actual cycle number and put the number into EDX and EAX. And using this code, we essentially copy the number to this high and low to these two memory locations. So this is the move instruction. This is to move the copy the value of this EDX to this argument, which is this location pointed by high. And similarly, the other half of the cycle count will be put into this low register, this memory location pointed by low. Okay. And then we can use code like this to calculate, given the old cycle number and new cycle number, we'll do a subtraction, and then we'll return the counter in terms of the elapsed cycles. Okay, so with these two APIs, start counter and get counter, we will be able to get the elapsed time in units of cycles. So we can do that, and then let's assume the time function is we want to count the number of cycles for one execution of this function P. Okay, so we start timer, start counter to record the first set of high and low registers representing the current counter value. You execute this P function, and then you again get the new cycle count, and that will determine the difference, which gives you the number of cycles this function has taken to execute. So it looks okay. So is there a potential problem? Especially if this function is pretty small, pretty short. So that's the overhead we were talking about earlier. To execute these lines of code, that would also themselves will take some time. So the number of cycles that you capture as a difference may not be, so might have some big variance with respect to this time function P. So you want to deal with this overhead and also the cache effect. So what we can do is we will execute a certain number of times for the P function to repeat itself. So we'll what we do here is we will repeatedly executing this P. Now the times we want to repeat is going to be increment until we get to some point the measurement difference. Let's see here. Okay, so this is where we execute the first time, the P function. We get counter, and then we will execute this P for this many times. So the CNT is first one time. We'll get the counter, and then we will calculate the number of times that this P function has been executed, and this is the average over the number of times that is executed, and then we'll increment the total number of times that this function is executed. We repeat this until this has reached to a minimum number of times. Then we can confidently say that we have executed P for, let's say, 50,000 times, and that will give us very good confidence on the overall execution time, because we amortize the overhead from getting these counters. So this example of determining the clock rate of a processor. So we use the counter number. We count the number of cycles required for a fixed number of seconds. Let's say we sleep 10 seconds here between the start counter and the get counter. So what we will have is the number of cycles will be used to divide the fixed number of seconds, and that will tell you the frequency of this processor. So you can use simply count the cycles for one-time execution of this function, but that will also that can be also improved by repeating the time for a longer period to amortize the overhead of the cycle count. So what we showed in some examples, do this one, yeah. The instrumentation may incur overhead, so it's better to measure long enough code sequence to compensate that. And the cache effects may skew the measurement, so it's a good idea to warm up the cache before making these measurements. We also need to be careful about multitask effect, because counters may keep going when a task of interest is inactive, and we need to make sure the task is locked to a single core when you do this cycle count measurement. And also the power management effects, make sure that the CPU speed does not change during your measurement.